Hello everybody. Let us discuss about the Fourier basis states in quantum Fourier transform. A multi-qubit state is represented as ket of m is represented by n qubits. So these q0, q1, qn minus 1, these are the qubits which constitute this quantum state ket of m. And its decimal equivalent can be found out from this formula, which is basically the general formula to convert a binary number to a decimal number. So therefore, if the quantum state is ket110, its decimal equivalent will be 6. Then this will be calculated like this, because the weight at the most significant qubit location, which is 1. So this location has a weight of 2 raised to the power 2. So therefore this 1 will be multiplied by 2 raised to the power 2, middle one will be multiplied by 2 raised to the power 1, and this 0 will be multiplied by 2 raised to the power 0, so which leads to a decimal value of 6. Now so ket m is referred to as the basis state generated by the encoding of the number m. The product state of 3 qubits can be visualized on the Bloch sphere. So we can visualize the product state as on the Bloch sphere, because a Bloch sphere can represent 1 qubit only. So therefore we need 3 Bloch spheres to represent the state of these individual qubits, right? And all these 3 qubits form a computational basis, ket 00 up to ket 111. So there will be which I mean to say is that since there are 3 qubits, so 3 qubits will form how many combinations? 8 combinations are possible. So 8 combinations are possible. Those 8 combinations will be termed as the computational basis, like ket 00 up to ket 11, ket 001, ket 010, and so on, and that will end by this ket 11 state. And the quantum superposition state will be consisting of the linear combination of these eigenbases, right? Like for example, I just scrubbed it, but I will write it once again. For example, let's say ket psi is this state. So let's say this state consists of alpha ket 00 plus beta ket 001, or plus maybe one more, we can take ket 11. So this quantum state consists of these 3 eigenbasis states multiplied by the coefficients, and these coefficients are complex numbers, and the mod of alpha square or mod of beta square or mod of gamma square, these values will give the probability with which the particular eigenstate will come after we do the measurement. That means after measurement, the quantum state ket psi will collapse to one of the eigenstates depending on the probability. So these 8 possible eigenstates are termed as the computational basis, right? It is very important to understand what do we mean by the computational basis. So in the case of if the multiple qubits are 2, in that case there will be 4 computational basis states, and these 4 computational basis states can be used to form a quantum state with linear combination, and using the complex numbers as the coefficients, right? So these product states, like for example here it is ket 110, can be visualized by the state vectors of 3 qubits in the z. So these computational, so this is also very important. These qubits are actually the eigenbases are, so in a Bloch sphere, so let's say this is the Bloch sphere. So eigenbasis we use is the z eigenbasis, right? What do we mean by the z eigenbasis? In that case, if we use a single qubit, one of the eigenstate will be ket 0 and the other eigenstate will be ket 1. So this ket 0 and ket 1 will constitute a computational basis for single qubit, and these computational basis will be governed by the z direction, ket z direction. So these are poly z computational basis we will call. If we want to get the poly X quantum basis, that will be represented by ket plus or ket minus, and similarly there will be a different basis for if we use the y direction as the computational basis. But let us stick to the z direction computational basis. So in that case, a single qubit will have computational basis as ket 0 and ket 1. The next qubit will have again ket 0 and ket 1, and the third qubit will also have ket 0 and ket 1 as the computational basis. Together they will form the product state. So therefore ket 0 0 0 is one eigenstate, ket 1 1 1 is another eigenstate. Like this there will be 8 eigenstates using which we can create the quantum state, the resultant quantum superposition state. Now if we, let us say, so these three blocks of spheres actually represent the state vector is pointing, is coinciding the positive z axis. So that means this represent a ket 0 value. So this second qubit also is ket 0 value, and third is also ket 0 value. So the product state is actually the product state that is being represented by these block spheres is basically what this is ket 0 0 quantum state, represented by from where this ket 0 0 has come, because the state from the state vector location, right? So this is like this, the state vector, using the state vectors we can represent all the possible eigenstates, all these 8 possible eigenstates. So basically what the important point to be understood here is that the computational basis. So computational basis I am considering is the z direction quantum is the z direction computational basis, which are governed by the positive z axis and the negative z axis, right? So these are termed as the poly z computational basis. Now let us try to understand the Fourier basis, because this Fourier basis can be understood only in the context of computational basis. Once you understand computational basis, then only you can appreciate that what is Fourier basis. Now let's try to look into Fourier basis. In Fourier basis, let me take the pointer. Yeah. In Fourier basis, the states are represented via qubits in the xy plane of the block sphere each time. Now, each time the state vector of individual qubits is rotated by a certain amount, right? So, in the Fourier case, the computational basis or we will term those computational basis as the Fourier basis will be represented by the positive x-axis or by the negative x-axis, and the state vector will lie in the xy plane, right? So that will, the position of the state vector is actually will determine the rotation will determine the rotation by which the state vector will be rotated in the block sphere. And how the state vector rotation will take place, so this is given by alpha subscript j to m pi divided by 2j. So if there are 3 qubits, so j will represent the position, j will represent the specific qubit, whether 0 1 2 like that. So in this case, so this is ket plus axis and this is ket minus value. So this is positive x-axis and this is negative x-axis. Now our computational basis, we will call these computational basis as the Fourier basis, right? So this is along the positive x-axis or negative x-axis. So in that case, depending on the weight of the qubit, the rotation will take place. So the third qubit Q2, which is the least significant qubit, will rotate 1/8 of a turn counterclockwise with each progressive number. The next Q1 will rotate the state vector by 1/4 of the full turn, and the first qubit Q0 rotates half of a turn for each increase in the number. So that's what these arrows are showing, the rotations that will take place depending on the weight of the qubit. Now The Fourier basis is the eigenbasis of the, so these Fourier bases are basically used in the quantum Fourier transform. We are interested in understanding the Fourier basis because we want to thoroughly understand the quantum Fourier transform algorithm. So basically what happens, it is obtained, now these Fourier bases are obtained by multiplying the QFT to the computational basis. Now what does that mean? Now let us say ket J represents the computational basis, as I have just explained the computational basis. So ket J is a generalized version of the computational basis. If you are considering a single qubit, in that case ket J will have value ket 0 or ket 1. If we consider two qubits, ket J will have value ket 0 0, ket 0 1, ket 1 0 and ket 1 1. So this capital N represents the number of computational bases, and small n is the number of qubits. So number of computational basis states will be equal to the 2 raised to the power n. So basically number of qubits, it is 2 raised to the power number of qubits will give me what? Will give me the number of eigen basis states. And how are we getting the Fourier basis? We are multiplying by applying the QFT. This is the quantum Fourier transform formula. We are applying the QFT formula to the computational basis and we get the Fourier basis. So ket K tilde represents the Fourier basis that we get after we apply the quantum Fourier transform to the computational basis. Like for example, if we have capital N computational basis, so that means our J value will vary from 0 to capital N minus 1. So there will be capital N computational basis states. That means ket of J will be turn by turn will get value ket 0, ket 1, ket 2, ket 3 up to ket N. So therefore, and that those values will be multiplied by the that means we apply the quantum Fourier transform on those values, and for each value, for each computational basis state, we get an equivalent Fourier basis state, which is given by ket 0 tilde, ket 1 tilde up to ket n minus 1 tilde. So these are known as the Fourier basis states after we apply the quantum Fourier transform to the computational basis. So these are what are these Fourier bases? So these are uniform superpositions of computational basis states, each with different complex phases, because there is a what does this quantum Fourier transform do in this case? It introduces a phase term here, which is the e to the power 2 pi I jk divided by n, right? And why I was mentioning the x-axis basis, if let us say there are two quantum basis, if there are let us say two computational basis states, one is ket 0 and the other is ket 1, right? Let us say this is our computational basis set. Now how do I get ket 0 tilde? These are the Fourier bases, and ket 1 tilde, right? So in single qubit case, as I said, this will be given by, so ket 0 will be equal to ket 0 plus ket 1 under root 2, right? And with some specific phase value. In the same way, we will get ket 1 with multiplied with certain phase value. So let me just no, I don't have for this. Okay, for more qubits I will show you when I will proceed with the lecture. But so why I am referring this to the x-axis, because if you take the Fourier basis, if you try to find the Fourier basis using these two computational bases, the Fourier basis, that means ket 0 tilde, you will get it equal to ket 0 plus ket 1 divided by under root 2. And the second Fourier basis that I will get from ket 1 is ket 0 minus ket 1 by under root 2. That is basically ket plus and ket minus bits. Alright. Let me just erase these values. Yeah, okay. So let's try to understand the Fourier basis further. So we can represent, so this is the quantum Fourier transform formula. Basically the formula that is the quantum Fourier transform that is applied to the computational basis state. Now this formula can be represented using a matrix also, as we used to represent the discrete Fourier transform in our signal processing course. So though we can in the same way write a QFT matrix also, where the f subscript capital N maps the computational basis to the Fourier basis, right? So what is this? So this formula, except this cat J state, will be represented by this matrix, right? And these omega square, omega, and these are known as the twiddle factors, and omega value is given by e to the power 2 pi I is the iota value, which is the under root of minus n divided by capital N. So this is our omega, and omega square, omega to the power n minus 1 will be calculated from this omega value. So this is the matrix that we will use. Now let us take the example with n equal to 4. That means 4 basis states are there. So if capital N is equal to 4, what is the computational basis? The computational basis will be cat 00, cat 01, cat 10 and cat 11. What is the, after applying the QFT, what output we will get? We will get the Fourier basis. That means we will get cat 00 tilde, cat 01 tilde and so on. So or that we can call, if we try to represent it in terms of the decimal value, we will represent it like cat 0 tilde, cat 2 tilde, or cat 3 tilde and cat 1 tilde also, right? So let us see. So this is the QFT matrix that we obtain using this generalized QFT matrix. Here we substitute capital N to be 4, and we will calculate, if we calculate if we take the twiddle factor value as 2 pi I divided by capital N will be equal to 4. So we will get this relationship, these matrices, this matrix f of 4 equal to 1 by 2, and these element values we will get after applying capital N equal to 4. Now let us apply this quantum Fourier transform matrix to cat 00 computational basis state. So that means we will take this matrix and we will take this cat 00 state. So what is cat 00 state? So cat 00 state is basically a column vector 1 0 0 0. So this column vector will be multiplied by this matrix F4, right? And what is the result that we will get? We will get the quantum Fourier transform of the computational basis cat 00. So and we get cat 0 tilde, which is in the Fourier basis corresponding to cat 00 computational basis state. So there is a transformation that is taking place between the computational basis and the Fourier basis using the quantum Fourier transform formula or the quantum Fourier transform matrix. Similarly, we can get for cat 01, cat 10 and so on. So we will get equivalent Fourier basis from the computational basis. So therefore, the Fourier basis is given by cat 0 tilde, cat 1 tilde and so on. Now the computational basis lies along the z-axis of the Hilbert space, and the Fourier basis forms a rotated basis where each vector is a superposition of all the basis states with different phase gradients. So what is this equal to? Every Fourier, when you multiply F4 with either 0 0 or 0 1 or 1 0, so we will get the rotation of the state vector, right? And it will be a uniform superposition. Like for example, if you consider this output 1 by 2 of 1 1 1, this represents the equal superposition of all the 4 basis states, right? So therefore we get a rotated basis where each vector is a superposition of all the basis states with different phase gradients. And let us see We will see the phase gradients also. What is the meaning of phase gradients? Once I try to I try to dive deep into the Fourier basis states. Let us have a even deeper understanding of the Fourier basis, because this is very important to understand, to ultimately understand the quantum Fourier transform algorithm, which is an algorithm used in most of the quantum algorithms which are being researched, or being people are working on those algorithms. So it is very important to understand this concept. So in an n qubit quantum system, the computational basis consists of so these are the computational basis. I hope you now understand quickly what do I mean by the computational basis, what do I mean by the Fourier basis, how do we get Fourier basis from the computational basis. So these basis states are localized. This is very important. These basis states like ket0, ket1, these are very localized. So what do I mean by this? For example, if you have a 3 qubit quantum system or quantum state, now how this basis value will be represented? So this will be a column vector at this position 1, and rest of all the positions will be 0. So therefore, the value 1 is very much concentrated, localized. Localized means to a particular qubit position, to a particular position. Not the value of 101 is not spread across all the basis positions, but it is localized to a particular value, which is 1. So that's what I'm trying to say here. The basis states are localized. Each represents a single definite binary configuration. A localized basis state is the one that is concentrated entirely in a single classical configuration with no spread or superposition. So let ket x, as this is the example that I'm trying to say. So this value is, this computational basis is very localized. But once we consider the Fourier basis, which is well contrasts to the computational basis, because that will be spread across all the basis states. Now let us try to find out the Fourier basis. So we know that this is the formula to find out the Fourier basis. So let us consider the case of 3 qubits. That means ket x, x consists of 3 qubits. So therefore ket x can take value from ket 0 to ket 7, right? And let us try to get these Fourier basis values. Let us, and as an example, let me find out ket of f1. So in this case, k value is 1. So once I substitute k equal to 1, capital N will be equal to 8. In that case, this will be x will vary from 0 to 7. This 1 over under root n will be giving me 1 over under root a. So therefore, the value of 1 over under root 8 comes here. And what else you get after you apply this quantum Fourier transform? You get ket 0, ket 1, ket 2, ket. These are the computational basis. So these are the, for a particular value of the Fourier basis which we are trying to calculate it for f1. What do I get? I get the summation of all the basis values with a phase value attached to each computational basis value, e to the power iota theta, e to the power 2 iota 2 theta. So these are the phase gradients which come along with the computational basis states to give me a Fourier basis state, right? So this is the difference between the Fourier basis and the computational basis. So a computational basis state lives at one point. We know that as I have just explained, it is a localized configuration, but a Fourier basis state lives across also. It lives across all the basis, all points. So this is delocalized. It is spread over all the points, all the basis, computational basis points. So physical and mathematical insights. So localized is position like computational basis states behave like delta functions, as delta functions are very localized at a particular axis equal to x naught. So they behave like that, and localized configuration they will result into. But Fourier basis, so the computational basis which is localized behave like a position like if we take the quantum characteristic or quantum property, so it behaves like a position, it behaves like a position characteristic of the quantum mechanics, whereas the Fourier basis behave like a momentum type of quantum behavior, which is a wave like behavior, and the Fourier basis behave like like plane waves e to the power iota kx and spread across all x. So this is same duality as position momentum in quantum mechanics. So what is the duality here? It is the position eigenstates which are localized or the momentum eigenstates which are delocalized, and these are plane waves. So why this matters? The localization of computational basis states allows easy classical like interpretation. This is, I am talking about the computational basis states. But what happens in the Fourier basis? The Fourier basis encourages interference because of these phase gradients. Whenever the phase aligns with the other phases, so it will result into either constructive interference or destructive interference. So that is what I am trying to say here. The Fourier basis encourages interference and encodes periodic patterns. So see, the Fourier basis will encode the periodic patterns and enables quantum speedups. Of course, because this is a superposition state, so it will enable quantum speedups, and it will encode periodic patterns. So therefore this quantum Fourier transform algorithm or the Fourier basis states will be used to determine the period of period finding algorithms. So these this type of basis is used. So the computational basis states, in general, if we use the positive z-axis and the negative z-axis, so cat0 will be the north pole position, cat1 will be the south pole position. This is in terms of the Bloch sphere actually. But in the case of Fourier basis, the Fourier basis is essentially the Hadamard or x basis. As I was just trying to explain you, positive cat of positive qubit value is 1 over under root 2 cat0 plus cat1. You can find out these values if we apply this formula using the appropriate computational basis. So you will get corresponding to cat0 you will get this value, corresponding to cat1 you will get this value. So these states are eigenstates of the poly x operator instead of the poly z. So on the Bloch sphere, cat of plus vector will point along the positive x-axis, and cat of minus vector will point along the minus x-axis, plus axis or minus x-axis, right? For n qubits, the QFT generalizes the idea and it maps the computational basis states cat x to a superposition of all the basis states weighted by the roots of unity. Of course, from where, what do we mean by the roots of unity? Roots of unity will be obtained basically from the Twiddle factor values. Let me just show you. Yeah, so these are basically, this will probably give me the roots of unity, right? So that's what this particular roots of unity word is coming here, right? So Fourier basis, so therefore Fourier basis is literally the output basis of the QFT, and in general this example I am trying to explain for n equal to 2, which is basically cat plus or cat minus. So that's what is the concept of the Fourier basis states and the computational basis state. Fourier basis states we obtain after we apply the QFT algorithm to the computational basis state, and we have also seen that what is the inner value, what are the inner values of the Fourier basis states, and how they align, the Fourier basis states align themselves along the positive x-axis or minus negative x-axis, whereas the computational basis states align with the positive z or negative z-axis. Thank you.